Okay, so I checked the homework over the weekend, and I guess what's most of the issues it looked like I saw were happening from the book problems, the 15 through 46. If there's a couple of those that you guys would like to do to start, we can start by doing a couple of those. And I'll do my best to walk through these slowly and clearly so that we can all feel like we can follow along and kind of carry on with what's going on. So if you have one that you'd like to see done, again, just type that into the chat and we'll kind of attack those one at a time. So first up is 17, which just says that tan of x is equal to 1. So I'll go straight ahead and apply my inverse. So what I'm looking for is a place where tan inverse is 1. Remember that tangent is y over x. So I'm looking for some place where on the unit circle where the x and y coordinates are equal. That implies that y over x would be 1. So if I go to my unit circle, I might as well just kind of copy and paste this in because we'll be probably going back and forth to it here a little bit. So there's two places where I see the x and y coordinates are the same, here at pi over 4 and here at 5 pi over 4. So those are my two answers for 0 to 2 pi, because those are the only two places on the unit circle where the x and y coordinates are identical. I can then extend this into infinitely many cases by just tacking on a 2 pi at the end, again where k is an integer. But if I look at this for a moment, notice the distance between these is pi units, which is half the unit circle. So like I have an answer here, I go here, that's pi, and I go back here, that's pi, and then here I'd go another pi. So every answer I'm getting is really just pi units apart. So I could really kind of condense these two answers together into a single answer. Now, you didn't need to do that had you left it as two separate answers. That's still correct. But if you're looking at like a multiple choice test or something, they would not have listed it as two separate answers. They would have condensed it into a single response, which is all that I've done there. It's still the same answer, just briefer. There's A, that's B. For C, we're looking for negative 2 pi to positive 2 pi. So I know that 0 to 2 pi is in that interval, so my answers for part A are still going to be answers for part C. But I also need to worry about the stuff then from negative 2 pi to positive 2 pi. Well, that's easy to find. I can just go basically this way on the unit circle to get to those two answers, which is really the same thing as subtracting 2 pi from each of them. So if I subtract 2 pi from 1/4 pi, I get negative 7/4 pi. And if I subtract 2 pi from 5 pi, I get negative 3/4 pi. And then for part D, our answer is negative pi to 4 pi. So I know that my answers from 0 to 2 pi will still be answers for D. I know some of my answers from negative 2 pi to 0 will be answers for D. Negative 7 pi over 4 is less than negative pi, so that one won't work. But negative 3 pi over 4 is bigger than negative pi, so that one I should keep. And then I'm also going to get possible answers from 2 pi to 4 pi. So to get those answers, basically what I would have done is I would have gone around the unit circle once till I got to here, which is basically just like adding 2 pi to each of these answers. So 2 pi plus 1/4 pi is 9/4 pi, and 2 pi plus 5 pi is 13/4 pi. So those should be my answers for D.
Wait, why is it, are we allowed to talk?
Yeah, go ahead.
Okay, I thought we had to use the chat or something.
No, it's okay.
Where'd you, I'm sure I missed something, but the 2 pi plus 5 pi you said?
So
where is that?
5 pi over 4 plus 2 pi gave me 13 pi over 4.
But why plus 2 pi?
So all of my answers are going to be coterminal to the answers that I found for part A. Any other answer for any other interval, the only possibilities are things that are coterminal to the part for my answers in part A. Is that okay? Or no?
No, I don't get it.
Okay, so the only place where I'm going to have answers are where the x and y coordinates are the same, right? Were you okay with that conclusion? That we got way back here.
That's a rule.
Well, if tangent is y over x, and we're looking for the place where tangent is equal to 1, the only way that can happen is if the x and y coordinates are identical, right?
Is that a rule?
Well, if I take two numbers and divide them, and they equal 1, the only way that can happen is if they're the same two numbers, right?
Right.
That's the only way you can get 1 with division. Do you agree with that?
Yeah.
That's all I'm saying here.
Well, how did you get there? It's like...
Well, the definition of tangent is y over x, and the tangent in this case is equal to 1.
So it would have to be the same to equal 1. Yeah. So you sub it out for x and y and see what equals 1.
Yeah, so I just looked at my unit circle, and the only place where the x and y coordinates are the same are those two places that I've highlighted. Okay there?
I think so, sure.
Okay. So all of my answers are going to land on those places on my unit circle. So like that's an answer at 5 pi, or pi over 4. But like that would also be an answer at pi over 4 plus 2 pi. Or this would be an answer, pi over 4 minus 2 pi. Or I could go around more than once in either direction, but any answer I get is going to land either at this pi over 4 spot or 5 pi over 4 spot, something that's coterminal to those locations. So I'm just going to be adding or subtracting 2 pi from those answers to find more answers. So that's what I was doing there.
Okay.
Is that okay? Ben, you're happy with what I did there, though? Also, this was your question, right?
Yeah, I just understand part D. That's basically it.
Okay, but you feel you're okay with what I did to get part D, though?
Yeah.
Okay.
Yeah.
Yeah, of course. Jesse, you wanted to do 38?
Yeah.
Sure. Okay, so 38, we noticed that we have two different trig functions. We have sine and cosine going on here. So in order for me to solve this, I really need to condense this into a single trig function. The trick here is going to be to turn it into, in this case, I'm going to turn it into tangent by dividing both sides by cosine pi over 3. So I'm going to have sine squared pi over, or x over 3 divided by cosine squared x over 3 is equal to 3. Now sine over cosine is tangent, so I can just turn that into tangent squared. X over 3 is equal to 3. And we'll square root both sides. So tangent of x over 3 is equal to plus or minus square root 3. I'm going to break that then into two separate equations. One for the positive and one for the negative. And then we'll do the tangent inverse. And remember that tangent is y over x. So in our case, if we're, say, looking at the positive square root 3, that would imply that y over x is equal to the square root of 3 over 1. Now, the y being the square root of 3 and 1 being the x is not a coordinate on our unit circle. But if I say multiply the top and bottom of this fraction by 1/2, I get root 3 over 2 over 1/2. And this is a location on my unit circle where x is 1/2 and y is 3/4, or square root 3 over 2. If I go back and I look here, so x is 1/2 and y is the square root of 3 over 2. And it could also be, since it's y over x and we're getting a positive number, it could have also happened if both of these were negative. So that answer, I have pi over 3 and 4 pi over 3. And then for this one, I'm going to be looking for the same locations, but one of them is going to be positive and one's going to be negative. So I could have x is negative 1/2 and y is positive 3/4, or x is positive 1/2 and y is negative root 3 over 2. I think I said 3/4 before and I meant root 3 over 2. My apologies. So that's 2 pi over 3 and 5 pi over 3. And then because we have a coefficient on the x, we have to be careful here. We have to write this as our infinite answer first. That was supposed to be 4 pi over 3, excuse me. Because those aren't necessarily actual answers yet. Oops. Ugh. All these fractions, I keep writing down things wrong, Jesse. Okay. Now to get the x by itself, I have to multiply each side by 3. So that's going to give me pi plus 6 pi k. This one's going to give me 4 pi plus 6 pi k. Oops. this next one is going to give me 2 pi plus 6 pi k. And this one is going to give me 5 pi plus 6 pi k. And now I'm finally ready to answer part A. So the only way that I'm going to get a positive number is if k is non-negative, since 6 pi is bigger than 1 pi, 4 pi, 2 pi, or 5 pi, right? And the smallest non-negative number I can have is 0. In that case, this would turn into pi. That's between 0 and 2 pi. This one would turn into 4 pi. That's too big, so I'm going to ignore it. This one would turn into 2 pi, but you'll notice that it's a parenthesis on the 2 pi and not a bracket, so 2 pi is not included in the interval that we're solving for. So I'm going to ignore that one. And then this one would turn into 5 pi, which is also too big. So my answer for part A is just pi. This stuff is my answer for B. There's possible opportunities for condensing, but I'm not going to worry about it right now because it's a little bit trickier because it's a 6 pi k at the end. But I think you can combine these two and make it plus 3 pi k, and similarly these two. But I'd have to like draw the picture and think about it for a second. C is negative 2 pi to positive 2 pi. So I know my answers for part A are going to be an answer. I remember when k was 0, I got 2 pi from this answer. But this one gave me 4 pi, which is too big. This one gave me 5 pi, which was too big. So that's everything between 0 and 2 pi. Now we have to look at the negative stuff. So we'll do k equals negative 1. This one would give me pi minus 6 pi. That's negative 5 pi. That's too small. This would give me 4 pi minus 6 pi, which would be negative 2 pi, and because it's a bracket, that one is okay to take. And this one would give me 2 pi minus 6 pi. That's negative 4 pi. That's too small. And then this one would give me 5 pi minus 6 pi. That's negative pi. That's one will still work. And if I make any of these any smaller, they're going to just be too small, right? So that's all of my answers for C. And then my last interval is negative pi to 4 pi. So I'll take everything from my previous answer that fits in that interval. So that's everything except for the negative 2 pi, because that was too small. But I can go all the way out to 4 pi here. Remember when this one was 0, this gave me 4 pi. But I have a parenthesis at the end rather than a bracket, so 4 pi is even too big. When this one was 0, it gave me 5 pi. That's also too big. This one I already have at 2 pi. This one I already have at 1 pi. If I add 6 pi to either of those, that's also going to be too big. So this is it for my answers for D.
Mr. Goy?
Yes.
Wouldn't 3 pi work too?
How are you going to get 3 pi?
Because, like, for B, one of your answers, you got, like, x equals 5 pi plus 6 pi k. So can you do, like, 5 pi minus 2 pi?
No. So you have to add and subtract by 6 pi's.
Oh, yeah. Okay.
Because it's not plus 2 pi k. You have to go, it's way stretched out. Like this is one where, you know, like
okay.
You had it looked like this before, now it looks like this. You know what I mean? So the answers are way spread out from a graphical standpoint. But yeah, that's why we do the infinite part first when we have a coefficient on the x, is because not every you're gonna get less answers or more answers than you maybe expected, because coterminal now is different than adding 2 pi. In this case, coterminal is adding and subtracting 6 pi.
Okay.
So, yep, good question though, for sure. Jesse, are you happy?
Yes, thank you.
Okay. 26 is next. And Dan, this will be a good one because it really combines the previous 2 questions pretty nicely. So similar to 38, we have sine and cosine. So I'm going to do the same trick that I did before and divide both sides by cosine. When I divide cosine x by cosine x, I just get 1. So that just turns into tangent of 1, which I believe is the same then as number 17, which we did as the first question. So that was quite a bit of serendipity. I'm just gonna recycle all the work that we would have done on 17 to answer that part. Is that okay, Dan?
Yeah, I got that.
Okay. Not a very satisfying answer, but like that's a very mathematician-y answer where it's like, I did this already. Just, it's the same as that. Which, if you wrote it on your paper for your homework, I would have been okay with. Because it's the same problem. Cool. So we have one more topic to talk about here in this chapter. And about proving identities. So we're going to be using kind of throughout our identity sheet. So I'm going to copy and paste that in here so it's easy for me to reference. If you wanted to have yours out so that it was handy to look at, we'll be using that throughout this lesson. So the idea with a proof, which is really what we're doing here, is you want to show why 2 things are equal, right? And the way we're going to do that is show how we get from one side of the equation to the other side of equation using only either basic algebra things or identities from our identity sheet. So in general, this is the strategies that we might use. I'm not saying you always are going to obey these or like they're hard and fast rules. But in general, these are the kind of the way to go about it, with the exception of number 1. And this is me asking from a style perspective. Where you have to pick one side of the identity to work on, and you're not done until it's identical to the other side of the identity. You can't do things to both sides, is basically what we're saying here. So you can't like add or subtract things from both sides. You can't multiply and divide things to both sides. That's not going to be okay. So when it comes choosing which side should I start with the more complicated side. So by more complicated, I mean that it has more terms. So if you have 2 things being added versus 2 things being multiplied, 2 things added is more complicated than 2 things multiplied. For instance, If you're not sure, turn everything into sines and cosines. So if you get stuck and you're like, boy, I don't know how to do this one at all, turn everything into sines and cosines. Usually it's easier to see what to do once you've done that. So the difference of two squares factoring pattern will often be helpful. In particular, you can use it to kind of set up a Pythagorean identity that might be something you want to use. Oh boy. Come on, one note. There we go. If you need to combine fractions, you need to make a common denominator. That's CD, is just me abbreviating common denominator. Boy, I always... And then always be mindful of where you're trying to end. Like what is it you're actually trying to get to at the end of the day. So none of these other than number 1 are like requirements. They're just things that would make life helpful. Doing, or could make life helpful, or make life easier in doing these. Okay. So we're just going to now do a couple of examples. I think I have 4 that I was planning on doing, and that's going to finish up this lesson. So we'll just kind of go through these 4 proofs. And then I will leave you guys to do some work on your own. Sound good? All right. So here's the first example we have. What we need to decide first and foremost is which side are we going to work on. And my advice in the beginning was to start with the more complicated side. 2 terms is always more complicated than 1 term. So I'm going to start with on the tangent plus cotangent side. Okay. Now there's no obvious way to add tangent and cotangent together. It appears that we're stuck. I know that, again, based on my advice, if I'm stuck, maybe I should try rewriting everything in terms of sine and cosine. So I'll do that. So I know tangent is sine over cosine, and cotangent is cosine over sine. I don't know why OneNote is being so laggy, but what else is new? And just FYI, what I used to do that was Q1 and Q2. So if you're looking at your identity sheet while I'm doing this, that's often going to be helpful.
How do you know which rule to use?
Well,
besides just
I knew that I was trying to turn everything in terms of sines and cosines, and the only thing that I have that with tangent in it that also has sines and cosines only were those 2 identities. So if you looked at your identity sheet, the only thing that has tangent in it and just sine and cosine is Q1. And the only identity with cotangent in it, with just sine and cosine in, was Q2. So that's why I chose those ones, as they were the only ones that I could have used that had just sines and cosines in it. Is that okay?
Sure.
Okay. So now I have these two fractions. Yes.
Sorry, do we have to say what, like, when we're proving them, do we have to say which identity we're using?
So I am going to do that when I give you guys the notes so that you guys can, if you're going back to look at things and you're like, how the heck did he do this? So you know what I did to do that. When it comes test time or whatever, I don't know, probably not. I think that it's a great idea for you guys to get used to just using like one or two identities at a time. Because again, if it's a proof, it's about like walking the reader through what it is that you did. So like communication matters, and the ability to communicate well matters there. So in general, no, but it could help if you're not very clear about things. It certainly adds a lot of clarity. I know that's a pretty wishy-washy answer, and you're probably not very satisfied with that, Dan, but
Yeah, no, I get it.
okay.
Thank you.
Yeah, you're welcome. Okay, so we have these two fractions now. So there's two terms. Keeping in mind where I'm trying to get to, I have one term. So I'm going to need to add these two fractions together. To add these two fractions, I need to make a common denominator. The common denominator in this case is just going to be sine times cosine. So I'll just multiply this first fraction by sine over sine. And I'll multiply this fraction by cosine over cosine, just to make a common denominator. I didn't use any identities here, so there's no identities to list. I'm just going to write down what I get in my next step. So sine times sine is sine squared. Cosine times cosine is cosine squared.
Why are we multiplying by sine and cosine?
We're making a common denominator,
Okay.
which in this case is sine times cosine. Okay, now let's again look at where we're trying to get to. So again, I should have secant times cosecant. If I go back and look at my identity sheet here for a minute. Come on. Oh my gosh, OneNote, you're killing me. I know that secant is really 1 over cosine, and cosecant is 1 over sine. So the denominator I have is good. Sine times cosine in the denominator is secant times cosecant. What I need to worry about is getting rid of the denominator, or getting rid of the numerator. So let's go back and look here. Remember, my numerator was sine squared times cosine squared. And I have an identity for that. Right? Sine squared plus cosine squared is 1. So that's what I'm going to do next, is I'm going to use that. So using P1, sine squared plus cosine squared is 1. And then my last step, I'm using R4 and R5 to turn 1 over sine into cosecant and 1 over cosine into secant. And I'm done, because the two sides are now the same. Well, really, I should write them in the opposite order, right? Because it was secant was first on the other side.
Can you scroll up a little bit?
Yeah, as soon as my thing stops lagging on me.
Sweet.
and we're done. Was that enough?
Mr. Kulik?
Yes.
Oh yeah, I just want to make sure. Let's say like I'm like condensing one side and I get stuck. Is it okay if I move over to the other side and try condensing it without moving anything over?
It is not.
So I can only work on one side?
Yes.
Even if I'm like not moving anything over?
Yes. Even if you're not moving anything over. You can't work on both sides and meet in the middle.
Okay.
Can you scroll up a little bit more, please?
Sure.
Okay, yeah, that should be good.
Okay. So let's do another. Okay. So on this one, when we look at these two, they look basically each side looks the same in terms of complexity, right? And to be honest with you, it probably wouldn't make much of a difference which side you started on. Technically speaking, the left side is more complicated than the right side because you have the sum or differences in the denominator, which is a little bit more complicated to deal with than the sum or difference in the numerator. So that's the one that I'm going to choose to work with, but you could have it would easily work. You know, it wouldn't be much different if you chose to use the right-hand side. So the first thing we'll do is look to see if there's an obvious identity to use. If you look at our identity list, I could turn cosine into 1 over secant, but now I have a fraction inside of a fraction. That feels worse to me. I could turn sine into 1 over cosecant, but again, now I have a fraction inside of a fraction. That feels worse to me. And that's it, right? There's nothing for 1 minus sine, but we have something that's close to 1 minus sine.
Are we doing the 1 minus sign or the 1 plus sign?
I'm working on the left-hand side.
Okay, cool.
So if I look at P1, if I had subtracted sine squared from both sides, I could say that cosine squared is equal to 1 minus sine squared. And that's what I'm going to try to make then in my denominator. Okay with that plan?
Could you repeat that, please?
So I just took P1 and I subtracted sine squared from both sides. That's cosine squared is equal to 1 minus sine squared. So I'm going to try to make a 1 minus sine squared in my denominator so that I can use this identity. So let's go back down and look at what I have. So I have this fraction, and I want to make its denominator 1 minus sine squared. Note that 1 minus sine squared is a difference of two squares, because 1 is something squared and sine squared is something squared. So I can create that by multiplying the top and bottom 1 plus sine x. So the cosine distributes. And now I could distribute the cosine through, but if I look at what I'm trying to get to, I already have a 1 plus sine x in the numerator. So I'm going to leave it as cosine times 1 plus sine x and hope that I can cancel that cosine in a future step. It wouldn't be the end of the world if you distributed the cosine through, like I had initially thought, but I took a second look at where I was trying to get to, and it's like, well, I'm just going to be factoring that cosine back off in a future step, so let's not go ahead and do that. Okay. So all I did there was just basic algebra, so no identity was required. Now that I have a 1 minus sine squared, I can use that identity, my P1 modified that I made, to turn that 1 minus sine squared into cosine squared. And again, let's look at where I'm trying to get to. I'm trying to end at 1 plus sine x over cosine x, which I'm pretty close to, right? I have a 1 plus sine x in the numerator and have a cosine squared in the denominator. But I can turn that into just a regular cosine just by reducing. And now they are identical, and I'm finished.
Real quick, how did you get the cos x times 1 plus sine over cos? Wait. Cos 1 point. Okay, never mind. Wait. You just multiplied the two problem, or two parts of the problem, right?
No.
No.
No, I multiplied the top and bottom by 1 plus sine x over 1 plus sine x.
To get a common denominator?
Nope. I did it so I could get this 1 minus sine squared that I had an identity to use with.
What?
There was no common denominator to make because I only have one fraction. I'm not trying to add two fractions, so there's no common denominator to make. Now, if you wanted to think about it as, I know what I'm trying to get to has a 1 plus sine x in it, and the only way I can get a 1 plus sine x from a cosine is by just putting it in there myself and multiply the top and bottom by 1 plus sine x. You could think about it that way. That's not an unreasonable way to think about it. Okay. Next one. Hopefully there's not a lot of argument about establishing the left side as the obviously more complicated side, right? If the other side is a single trig function, that's going to be pretty tough to get more complicated than, or less complicated than that. Now, if I look at this, it's already in terms of sines and cosines, right? Everything has a cosine in it. But I have this obvious two parentheses multiplied together. Let's just FOIL that out, right? It seems like it's begging for that to be, for us to do that. And if I combine like terms, I have a positive cosine x and a negative cosine x. So those canceled out. Leaving with a 1 plus cosine squared over cosine squared. And now this looks familiar, right? 1 minus cosine squared. I had something pretty similar to that just a moment ago. I had a 1 minus sine squared that I used something on. Let's go back and look at our identities. So again, if I take P1 here, and I subtract cosine squared from each side now, I see that sine squared is equal to 1 minus cosine squared. So that's what I'm going to use, since I have a 1 minus cosine squared here.
Mr. Coolett,
Yes.
did you FOIL the top? Like, how'd you get the 1 plus cosine x minus cosine x minus cosine x squared x?
That was me foiling the numerator, yes. So
Okay.
1 times 1 is 1. 1 times cosine x is positive cosine x. Negative cosine x times 1 is negative cosine x, and negative cosine x times sine, or cosine x is cosine squared x.
Okay, yeah, I get it now. Thank you.
Yeah, no problem. And then this should jump right out at you, right? We used this identity earlier. We know that sine over cosine is tangent. That was Q1. So sine squared over cosine squared must be tangent squared, which is what we're aiming to get to. And we're done. Our last example. So we have a sine squared x times cosine to the 5th x equals the quantity sine squared x minus sine to the 4th x plus sine to the 6th x. that quantity times cosine x. I would think that probably we would want to start on the right-hand side, although the left-hand side is still totally doable. If I look at the right-hand side, the piece that begs me for simplification is the sine squared minus sine to the 4th x plus sine to the 6th x. And what jumps out at me is that there's a greatest common factor of sine squared in each of those. So I would start by just taking that greatest common factor out. Oops, I need to make a little addition here. So I copied that down wrong. There should be a 2 in front of that sine to the 4th x in our problem. I forgot to copy, I copied it down wrong, so. Okay, so let's compare our two sides now. So I have a sine squared, and I have my sine squared there. So I'm done with the sine parts, right? I have a cosine to the 1st here, and I have a cosine to the 5th here. So this part here has to give me a cosine to the 4th, right? Because cosine times cosine to the 4th is going to give me the cosine to the 5th. So somehow that part there has to be cosine to the 4th. That's what I'm going to be working towards. Is everybody okay with that idea?
Sorry.
It's okay. I'm just waiting and seeing if we're to process, because I'm throwing a lot of stuff at you, and so I'm just trying to pause here intermittently to let you think about stuff, to make sure you understand what I'm seeing. Because again, doing one of these proofs, like you can copy all the stuff down, but if it doesn't make any sense to you while I'm doing it, it's not that helpful to have everything copied down, right? Okay. So that part, 1 minus 2 sine squared plus sine to the 4th x, is the only part that we really need to work on. If you look at that, what does that kind of remind you of? When I look at this, it looks a little like a polynomial, where if instead of sines, we just had a variable like a or something, right? And in fact, even though that's a polynomial, like a degree 4 polynomial, it's a pretty easy degree 4 polynomial to work with because it's in the quadratic form. You guys remember talking about last year in your Algebra 3-4 class, factoring polynomials that were in the quadratic form, where the degree of the 2 variable part terms, the degree was double. You guys remember doing that? That we can make like a second substitution and think about, oh, really, what if b is equal to a squared? So really I have 1 minus 2b plus b squared. And that we can factor as 1 minus b squared, right? So let's put all these ideas together now. So we said b is equal to a squared. So this I could think about as 1 minus a squared squared. We said a is equal to sine x. So that would be 1 minus sine squared x squared. And wait a minute, 1 minus sine squared x. We've run into that a couple of times already today, right? That was our modification of P1 the first time that we did that. 1 minus sine squared is cosine squared. And cosine squared squared, well, that's just cosine squared times cosine squared, which is cosine to the 4th. And cosine to the 4th times cosine to the 1st is cosine to the 5th. And that's what we were looking for.
Mr. Cooley,
Yes.
can you explain like the 1 minus 2a squared plus a to the 4th part, like the thing?
Yeah, so this is just me trying to justify how I'm factoring 1 minus sine squared plus sine to the 4th, because probably at first glance that doesn't look like something that you would know how to factor. So I made 2 substitutions in order to get this into a form that was easy to factor. The first substitution I made is like, okay, I'm just going to replace the sine x's with a variable. That variable is a. But when I do that, I notice that I have a to the 2nd and a to the 4th, which is not a quadratic exactly, but it's in that quadratic form. So I made a second substitution, replaced the a squareds with b. So a squared becomes b, and a to the 4th is a squared squared. So that just becomes b squared. And this was something that I can factor. 2 things that multiply to give me 1 and add to give me -2 is -1 and -1. So I have 1 minus b squared. And since b is equal to a squared, I replace the b with a squared. And since a was equal to sine x, I replaced the a with sine x, so I have 1 minus sine squared squared. Did that do it for you, Dan?
Yeah, I got it. Thank you.
Yeah, no problem. Again, like, not a super obvious factor. What might have been easier in this case would have been working on the other side first. So just for grins, if we had chosen to do the other side, the first thing I would have noticed is, okay, I have a sine squared here, but I have only a 1 cosine over here. So this cosine to the 4th, for other 4 cosines, I'm going to kind of separate off, because I know this part and this part now I've got. And maybe I noticed even that this has a greatest common factor of sine squared in it, which I already kind of have. So I just need to get this cosine to the 4th part to have only sines in it. And probably the easiest way to think about that would have been, okay, well, I just have 2 cosine squareds, because I know that cosine squared is 1 minus sine squared. And then if I multiplied all this stuff out, that I'm not going to write down, because again, this is me doing the same problem just from the other direction, you end up with what you're looking for. But I'm not going to show that multiplication right now. But if you foiled those out and then distributed the sine squared through, you'd get that exactly what you're looking for. And maybe it would have been easier conceptually to go from that side. And it's certainly no harm in like trying one side, and if you get stuck, to just cut bait and maybe like, okay, I'm just going to put a big X through this work and try starting on the other side and seeing if I can get to the other, doing it the other direction. There's no reason you can't do that. That's certainly something that's okay to do. So we're done. Those are the examples that I had planned for today. I don't want to keep you any longer. What I would like for you guys to work on for next time is 47 through 62. These are all identity proofs. Some of them are more difficult than others, so they're of varying difficulty. Some you can probably figure out right away, or that are very similar to things that we've already done. Some of them might be challenging. Again, to do these, my suggestion for you is to have your identity sheet out to look at while you're doing these. Those are the rules that you get to use aside from basic algebra stuff. And keep in mind the little guidelines that we pointed out at the beginning. They are often quite useful. Try not to get frustrated while doing these. It doesn't help. Just go slow. Try to use good algebra. Oftentimes the mistakes I see students make are just like basic algebra mistakes where we didn't make a common denominator, we didn't factor something correctly, or we didn't distribute something the right way, or and that can cause all kinds of problems and not being able to get something to work out. So try to be careful there. So we're going to stop here because I've taken enough time here. I ideally would like to spend less than